Okay, we're now going to look at a couple of examples where you may be asked to use Rolle's theorem or the mean value theorem. First, an example where our function is y equals sine of 2x and the interval is 0 to pi over 2. First question is, does Rolle's theorem apply on this for this function on this interval? A sine curve is continuous and differentiable everywhere, so it is going to definitely meet the first two criteria. The other thing that we need to do is evaluate this function at 0, and that's going to be equal to 0, and we need to evaluate this function at pi over 2. So the sine of 2 times pi over 2 is pi, and that is also 0. So all three criteria for Rolle's theorem are met. So we know that there will be some value of c where that statement is true, and that value of c will be somewhere in between 0 and pi over 2. So to find that value, we find the equation for the derivative. So that would be y prime, because this function is set in terms of y. Using the chain rule, we'll end up with 2 times the cosine of 2x, and we set that equal to 0. So the cosine of 2x will equal 0 if you divide both sides by 2. And then now, the way I suggest you think about this, since x is in the interval from 0 to pi over 2, then 2x would be in the interval from 0 to pi. You just multiply both of the endpoints of that original interval by 2. And so I'm going to solve cosine of 2x equal to 0 on the interval from 0 to pi. So I'm thinking about my unit circle. 0 and pi are located there and there. And I'm looking for angles whose cosine value is equal to 0. Well, that's going to happen when the angle is pi over 2. And that's the only angle that has 0 for the cosine value in the interval that we're looking at. So 2x is equal to pi over 2, x is equal to pi over 4. And you'll notice if you go back and think about that original interval, pi over 4 is in between 0 and pi over 2. Okay, the second question that we're going to take a look at involves the mean value theorem. Then for this function, 3 times the sine of 2x on the interval from 0 to pi over 4, the first thing we have to do is decide if the theorem applies. And it does, because a sine function is continuous and differentiable everywhere. So it's definitely going to be continuous and differentiable on the interval from 0 to 4. So since that's the case, our next job is to find the value of c that satisfies this equation. So there are some things we're going to need to know. First of all, we're going to need to know the derivative function. Using the chain rule, we'll end up with 6 times the cosine of 2x. We're going to need to know f of pi over 4, which will be 3 times the sine of pi over 2, so that simplifies to be 3. And we need f of 0, which is 3 times the sine of 0, or 0. So our job now is to set 6 times the cosine of 2x equal to 3 minus 0 over pi over 4 minus 0. Change in x divided by change in y. Simplifying the right side of that equation, we'll end up with 3 divided by pi over 4, and that then would be 12 over pi. Solving for cosine of 2x by dividing both sides by 6, I'll have 2 over pi equal to the cosine of 2x. Okay, we're going to do a trick kind of similar to what we did last time. The original interval for x was 0 to pi over 4. So for 2x, we're going to think about the interval from 0 to pi over 2. So thinking about the unit circle, I'm only allowed to look in the first quadrant. Now this is a problem where 2 over pi is not one of the cosine values of one of our special angles, so we're going to have to grab a calculator to be able to calculate the inverse cosine of 2 over pi. If you do that calculation in your calculator, you will find that 2x is going to be equal to 0.88068, etc. You round off to at least 3 places and I'm a happy person. Then solving for x, by dividing both sides by 2, you'll have 0.44034. And if you think about that angle, we just need to make sure that it's actually in the interval from 0 to pi over 2. Pi over 2 is about 1.57. So 0.44 is definitely between 0 and 1.57. It would be, you know, maybe somewhere around in there. Now there are a number of, well, there are a few consequences of the mean value theorem, for lack of something better to call them. And a lot of times we think of consequences as being bad things. A consequence is not always a bad thing. The consequences of the mean value theorem that we're going to talk about are actually very good things. And we're going to talk about them very, very quickly. Okay? The first one, a zero derivative implies a constant function. I'm not going to go into detail. It's actually proved for you in your textbook, but it's important for us to kind of make the connection that here, that if f is differentiable, and if f prime of c is equal to 0 at all the points of some interval, so the function is differentiable everywhere in this interval, and all the derivative values equal to 0, then that function is a constant function, or that function is constant, at least on the interval I in question. Okay. The second point, functions with equal derivatives differ by at most a constant. Okay, and you can think of some examples. For instance, if you had f of x is equal to x squared plus 2, and f of x is equal to x squared minus 2, and you differentiate both of those equations, both of those derivatives, I guess I should call that function g. Let's call that something else. G of x is x squared minus 2. F prime is 2x. G prime, also 2x. So we've got two functions here that have the same derivative. The only difference in those equations is the value of the constant. And that's what we're saying here in this second point. If f prime of x is equal to g prime of x, then the difference of f and g is c, where c is some constant. Alright, and the last point. It's the mean value theorem, and again, this is a fairly complicated proof. You can take a look at some explanation in your textbook. It's the mean value theorem is what makes it actually possible for us to say that a function is increasing when the derivative is greater than 0, and a function is decreasing when the derivative is less than 0. When we looked at that section earlier in chapter 4, we just kind of took a look at it and said, you know what, where we've got this function that's increasing, look at all these slopes, look at all these tangent lines, they all have positive slopes. To actually prove that involves the mean value theorem.